Hello and welcome to the presentation of our paper, which is Modeling Memory for Individual Re-Identification in Decentralized Mobile Contact Tracing Applications. So in this paper we focused on mobile contact tracing applications, so MCTA, which have been proposed as a possible solution to contain the pandemic, as they notified users who have been in contact with the positive users in order to be eventually tested. So there were roughly 4 different proposals, either with Bluetooth Low Energy or GPS, and either distributed or centralized. In this work we focus on Bluetooth Low Energy, MCTA, either distributed or centralized. So when mobile contact tracing applications were proposed, there have been a lot of privacy concerns about the possible identification of individuals, possible identification of locations, data leaks, etc. So even though those problems have been partially solved, in this work we present a novel attack, which is based on the memory of individuals. So the main idea that we explored is that each person may actually remember people and places, and if they are able to correlate those memories with codes from the mobile contact tracing application, they are actually able to understand who is the positive individual which is responsible for their notification from the mobile contact tracing application. We modeled the problem as a graph in which we have different time windows, and these are the time windows identified by the mobile contact tracing application, and in each time window you listen for codes and you can receive 0 or more. So apart from that, we also modeled the memory of the individual as the ability to remember people and places, and we leveraged the work from literature on this. And we also are able to prune the graph based on invalid connections, and we can do that with 3 possible operations. So basically we can identify positives in a graph when the number of people remembered in a certain time window is equal to the number of codes that you received. And the similar can be done for negatives. Of course, you have to invert them. And when you do that, it's also possible to prune edges. So basically when you are able to identify positive and negatives, you can simplify the graph, because you can remove possible connections which are not valid anymore. For instance, if you identify some negative people, they cannot have any code associated with them, and so on and so forth. Apart from that, we also identified 3 possible mitigation techniques. The first one is to use a variable time window, basically reducing the information sent by the server. The second one is to inject fake contacts or send multiple reports at once. And the third one is to use a variable contact tracing range based on the sociability of the individual, although this reduces the precision of the contact. So we use 2 real datasets. They are very similar. The only meaningful difference for us is that the Copenhagen dataset also reports the RSSI between 2 individuals, while the social evolution dataset doesn't. We applied the graph modeling that I just showed to Copenhagen and social evolution, and what it can be seen is that it's really easy to identify contacts based on current mobile contact tracing application, regardless of the density, regardless of the dataset. Then we evaluated our mitigation techniques. Here we evaluated the variable time window. On the left part of the slide you have the identification probability with a variable data length. So this is basically the amount of data which the server reports to users to check whether they have been in contact or not with a positive individual. And of course, if you report a lot of data, users are able to prune more edges in the graph, opposed to sending less data, which is more privacy preserving. And also adding more users to the report also limits the possibility to identify users, because basically if you send only 1 user, then all the codes that you receive are referring to that specific user. If you send more users, then you cannot correlate positive codes among them. Fake contact injection doesn't work really well, basically because you simply skip it. So if you can't associate it with a user, then you simply go on with the other ones. And for the variable contact range, this is just shown for Copenhagen, as I said, because for social evolution we don't have the RSSI information. The outcome here is that the more social you are, the better it is. So of course social means how many users you have around you, And to increase this value, the easiest way to do so is to reduce the RSSI threshold, so you can actually listen to more people. But of course, this also reduces the precision of the mobile contact tracing application. So to conclude, we identified a novel attack on mobile contact tracing application based on the memory of the individuals, and we have shown that these attacks is indeed possible, also with the use of real datasets. And among the 3 mitigation techniques that we propose, certainly the first one and the last one are the most effective, as the sociability has a huge impact on the possibility to identify users. And also the amount of data which is provided, because of course if you provide less data to the mobile contact tracing application, this might suffice to identify a positive contact, but it doesn't disclose too much. And this is also one of the easiest techniques to implement in real MCTA. So this is the conclusion. I thank you, and I'll take questions if there's any.